Okay, section 2-1. So last chapter we discussed 3 different parent functions: the constant, the linear, and what was the other one? Absolute value. All right, we're gonna learn a 4th one today, and they're called quadratics. So the parent function for the quadratic functions is y equals x squared. And just like any other time, when you don't know what a graph is going to look like, make a t-chart. So 0 squared, 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. Negative 1 squared, 1. Negative 2 squared, 4. Negative 3 squared, 9. So we put all these points on there. 1, 2, 3, 4. 9. All right, there we go. That is the parent function for the quadratic functions. When you graph it, it's called a parabola. And it probably would help if it actually went through the points. Okay. So a lot of people say it's sort of U-shaped. Just be careful with that. It doesn't just go straight up, because then it wouldn't be a function. It wouldn't pass the vertical line test. It's always expanding, and your x's can always increase. It's just that a small jump in an x results in a larger jump in a y the bigger x gets, or the closer x gets towards either positive or negative infinity. Okay, so this part right here is really just applying what we knew last chapter with the transformations. If we take this y equals x squared and you do whatever transformation happens, let's see. How about this? This one, and this one will all be reflected about the x-axis because of the negative out in front of your square. So those 3 narrow us down to this, and this. Okay. And then this one's going to take this graph and also move it 2 places to the right. So we're going to flip it upside down. And then once we do, we're going to move that 2 places to the right. So that's got to be choice D down here. All right, so we got it. This little C up here, that's going to go it's going to be upside down. Oops, why is it not right? Because this is going to go left 2 and down 2. So if I flip it over the x-axis first, then go left 2 and down 2, that looks like choice A. Got it. And then this one's going to go left 2 and up 2, which that's choice E. Okay, so the other 3, they're all right side up. This one does not have any sort of vertical stretch or shrink. It's just the normal size. This one has a vertical shrink by a factor of 1/2. This one's got a vertical stretch by a factor of 2. So one gets a little skinnier than usual. One's going to be a little... sorry, I got a yawn. Gets a little fatter than usual. And let's see what we're doing with the moving it around, because it'll be easier to tell the left, right, up, down than it will how skinny or fat it is. So like I said, this one right here, all we're going to do is go to the right. So out of the 3 that are left, that's definitely B. Okay. Choice D up here goes 2 to the right and down 2. 2 to the right and down 2. And see how it looks a little fatter than the other one? That's choice F. And this one, 2 to the right and up 2, but just a normal size parabola. That's choice C. And then we got them all. So we didn't have to plug in any points. It was just using what we know about transformations to help us figure out which of those functions it is. Okay. All right. So this is just out of the books so that you'd have really good notes, I hope. Just reminding you of what happens. I think we basically just went over that. So I'm not going to hit it real hard. This thing right here says let's describe the transformation of the parent function described by this. And then we're going to graph each on the same coordinate plane. So our parent function, I'm going to do it with a dotted curve. So up 2, 4, 3, 9. Okay, so there's it was written as f of x here. Okay, g of x, I'll do a different color. We're going to go 4 left and down 1. So if we go 4 to the left and down 1, that's where that point that's at the very bottom goes. And then see on the parabola, we went over 1, up 1. So over 1, up 1. Those points are going to be there. We went over 2, up 4. And then over 3, up 9. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. There is our new function. And just to double check, I'm going to make sure, like, I've got it going through the point -1, up 8. So if I go back up there and plug in a -1 to g, 3, 9 minus 1. Yep. It's going through a point that I thought it should go through. So it said, oh, describe. 4 left, down 1. We did their description. We graphed both. I think we got it all. Okay. All right. And then we talked about vertical stretches and strengths. We got the reflections. Again, that's just from the book, so your notes look nice and complete. And this one, we're graphing each function. Oh, there it goes. If it doesn't say you have to graph the parent function, I guess technically you don't have to, but it might help. So I'm just going to go ahead and do it on each. And I'll do it with a dotted curve. So that it's obviously not the one they're saying to graph. Okay, so there's our parent function. There's our parent function. All right, so we're going to describe the transformations. The negative is a reflection about the x-axis. And then the 1/2 is a vertical shrink by a factor of a half. Okay, over here, we've got a vertical stretch by a factor of 4 and up 1. All right, so let's go through here. Trade colors again. I like the purpley colors. Okay. So just imagine this dotted curve getting flipped upside down and vertically shrunk. So this point, when it gets flipped upside down, it's not going anywhere. If on the normal parent function you go over 1, up 1, this one's going to go over 1, up a half, but we're going to go down because we flipped it over the x-axis. And then if it was over 2, up 4, we're going to go over 2, up 2, because all the y's are going to be half as far away from the x-axis as they used to be. Instead of over 3, up 9, well, half of 9's 4.5. And then we could go another one. So if we did 4 squared, get 16. Half of 16 is 8. So we've got a curve. It looks like that. Here's g of x. And I've got mine going through 4, -8. Let's see if that works. If I did g of negative, or not -4, g of 4, I'd do half of 4 all squared, or half of 4 squared. So half of 16 is negative a. I'm feeling good about my graph. This one, okay, so we're just going to move it up 1. And then we're going to stretch it. So if we went over 1 up 1, now we're going to go over 1 up 4. So we'll have those points right there. And I'm not going to worry about the next one because where it was over 2 up 4, if I quadruple that, it'd be over 4 up 16. I'm going to run off the page. But I've got it going through 1, 5, right? So if I did h of 1, 4 times a 1 squared plus 1, 4, that gets to 5. It goes to the point I said it did. Okay, so a quadratic function is a function that can be written in this form, where we've got some number out front. So like if we go back and look at all these examples, you've got some number out in front of the square. And then you got an x minus some number, all squared, plus k. You don't want the a to be 0. If this were 0, you wouldn't have the x squared in here. So it wouldn't be a quadratic. So you can't have that be 0. But whatever that shape that results, we call it a parabola. Okay. The lowest point or the highest point, like that point right there, is the lowest point. It's called the vertex. If it had opened the other way, the highest point is called the vertex. Okay. So it doesn't have to come to a corner. Like it's not like it has to be like the vertex on an angle. It can be, we can call it a vertex, and we do on a parabola, even though it's a curve. You know, don't let this come to a point. It's not like a sharp vertex. It's a smoothed off corner. Not corner is not the right word. You can see what it looks like. So when you start talking about that a, it indicates whether it's a reflection or not. Because if a is positive, it'll go right side up. If a is negative, it'll turn upside down. And then it's going to talk about how much it vertically stretches or shrinks it. So if a gets greater than 1, it's a stretch. If a is between 0 and 1, or I guess technically, because if I'm just calling it a, it'd be between negative 1 and 1 and not 0. It would be a shrink. We're going to move it left and right and then move it up and down. Okay. And then we also have a line on a parabola. Like wherever you draw your parabola, there's a line that cuts it down the middle. So that if I folded it over that line, it's symmetrical on both sides. That's called the axis of symmetry. Okay. So if we're looking, let's just make it an example. This is going to be a parabola. It opens down. It's vertically stretched. It moves 2 to the right and up 5. So it's the movement up and down and side to side that affects where the vertex is located and where this axis of symmetry is. So if we go to the right and up 5, that's your vertex. And then if it turns down and it's vertically stretched, it's going to be skinnier. So the line that cuts it down the middle, it's going to sit there. So wherever that x value is on your vertex, that's going to be the line of symmetry cutting it down the middle. So if you've got this form right here, whatever the h and k are, that's your vertex, and x is h is the axis of symmetry. So let's just go label all those. And I always draw the axis of symmetry first because I like to put in the line that cuts it down the middle. So I'm going to get this ready. What's the axis of symmetry? Oops, can't spell. And the vertex. Okay, here you're not moving it side to side any. So your axis of symmetry is still just the y-axis. But you move it up 4. So axis of symmetry, x is 0. And then you go up 4. And there sits your vertex. So you get the x value out of the axis symmetry, and then you move up and down to wherever. And then if you had to graph it, because there's no vertical stretch, it's not reflected. Over 1, up 1, over 2, up 4, just the usual. There's your parabola. This one we're going 1 to the right and down 3. So when I go 1 to the right and start drawing in a parabola, there's the line that cuts it down the middle. And I'm going to go down 3 and put my vertex. It's opening up, usual shape, over 1, up 1, oops, over 2, up 1, 2, 3, 4, 1, 2, 3, 4, over 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. See why I like to have the axis symmetry on there? Because I'm just imagining flipping it over it. Okay, same deal here. I'm going to get my axis of symmetry and my vertex. Axis of symmetry and my vertex. This one, I'm going 9 to the left, so the axis of symmetry is at x is -9, which gets me the x value of the vertex, and I'm going up nothing. So there's vertex. And then all it's going to do is flip it upside down. So this side's running off the graph paper. 1, 2, 3, 4. This side, I could put some more and see it. Here, I'm not moving it left and right any, so the axis symmetry stays at x is 0, but I go down 7. So 0, -7, and it doesn't have any sort of reflection or shifts. Where am I down 7? 2 more. And we've got that parabola. Okay. Speed this up. Okay. We're not shifting in any, so axis symmetry is x is 0. Remember, this is a line that cuts down the middle. Oops, it does not look like a 0. And then we're going to go down 6. 1, 2, 3, 4, 5, 6. And it's a third as high as usual. So this is a third. That's kind of a weird thing to deal with. I think I would just, well, no, I guess I should make my point. So if it's over 2, it's usually up 4. So now it's going to be up a third of that. So 4 thirds. And then over 3, up 9, a third of that's 3. 1, 2, 3. And then I think I would just go ahead and plug in a 6. A third of 36 minus 6. A third of 36, 12 minus 6 is 6. So when I'm over 6, 1, 2, 3, 4, 5, 6. 2, 3, 6. And then I'd have a good point to line it up with. Okay. This one, axis symmetry, go 3 to the left, so it's at x is -3. 2, 3. Go up 2, so the vertex is at -3, 2. It's going to turn it upside down, usual shape parabola. So we'll go over 1, down 1, 2, 1, 2, 3, 4. 3, 9. That's going to put me at what? -7? Oop, I went over too far. And then I'm showing it going through 0, -7. So let's just check. -9 plus 2 is -7. Yep, I feel real good about it. All right, that's it.